Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to analyze impacts in two dimensions here and how to calculate a coefficient of restitution. So what we're looking at here, this picture on the left here, this is a snapshot in time before an impact occurs. So we've got two masses, A and B. Mass A is moving left at 6 meters per second. Mass B is moving kind of up and right according to this geometry here at 4 meters per second. For this example, we're going to have or assume these masses are the same. After the impact, it was given in the problem I looked this up at that mass B is kind of moving up and left at an angle 30 degrees with the y-axis as shown. The problem that I read stated that mass A moved parallel to the x-axis after impact. So kind of looking at this impact, I'm going to take a stab that mass A probably is moving to the right. All right, now when a velocity vector is unknown, you're perfectly free to pick a direction and just take a guess at it and let your answers sort it out in the end here. So if this direction is not correct, what will happen is a minus sign will show up. So as far as how we analyze impact, the first thing we always do when we analyze an impact is we draw a snapshot in time like I have right here, and you draw momentum vectors. Now whether this is a momentum vector or a velocity vector doesn't really matter. They're both in the same direction. The only thing that's going to change here is the the magnitude of the momentum vector. This velocity vector is 4 meters per second. The momentum vector would be mv would be 2 kilogram per second. I like to think of these as momentum vectors. Here's a momentum vector up and right. Here's a momentum vector to the left. Then you would always draw a snapshot of what the system looks like after the impact. So I would have mass A's momentum vector pointing to the right, mass B's momentum vector pointing up and left. And again, I'm going to go back and say that I kind of guessed on this velocity direction. Could be left, could be right. I'm going to just guess right and see what happens and move on. Right. What it is we're going to try to calculate here is the coefficient of restitution for this problem. So just a little reminder, coefficient of restitution is VB2 minus VA2 over VA1 minus VB1. It's important to know, though, that this applies in the normal direction for an impact and only in the normal direction. Right. I've already taken the liberty here to draw an important picture for this impact. Taking note that VA1 is to the left. So mass A's initial momentum does not have a y component. And in picture 2, it still does not have a y component, whether it's going right or left. That guarantees that the impulse acting on mass A is along this axis here. It cannot have a y component. So this picture, I've drawn the impulse acting on mass A to the right, and you could write that impulse as either like force times delta t, where this would be like an average force, or integral f dt. That same impulse acts to the left on mass B, and this allows me to define directions now. We've got the normal direction, the tangential direction. So if you were working this problem fresh, you would draw this snapshot, put in the momentum vectors. Draw the second snapshot after impact, draw momentum vectors and label them. And you always want to draw a picture of the contact time, the small dt when they're in contact, and draw the impulses. Right. Now there's a couple ways to analyze this problem. I believe we probably could just define our system like this, write a momentum conservation in the x direction and write another one in the y direction, and end up with like a system of equations for VB2, VA2. I'm going to take note of this. Taking a look at this mass and looking at this impulse, this does not have a tangential component. So the first equation I'm going to write is this: conservation of momentum for mass B only, up positive. And what allows us to do this is the fact that this impulse does not have a tangential direction. So we look at this momentum vector. It's going to be MBVB1. I want the tangential component, so I'm going to multiply that by 4/5. Right. Now I'm going to look at this picture. The tangential component of that momentum vector is going to be VB2 cosine 30. That's the component that's going to be along the y-axis or in the tangential direction. And again, taking note, because this impulse does not have a y component, we can put equality between these. Right. Now, in this problem, the masses are the same. They're going to divide out. I'm going to go ahead and solve this for VB2, taking note that VB1 is 4 meters per second. And I get, for VB2, 3.70 meters per second. And we go, yay, we calculated something, so we're happy. Whoops, smiley face. All right. This is one of the quantities that we're going to need to find the coefficient of restitution. All right. The next one we're going to need is this VA2. I'm going to go ahead and do that by looking at momentum in the x direction for the system now. See, I can't write a momentum equation right now for only mass A because of this external impulse. And we don't know the coefficient of restitution, right? If we knew the coefficient of restitution, a momentum equation in the x direction, I mean, basically that's what this is. It would be a momentum conservation in the normal direction, but we don't know the coefficient of restitution. So right now we cannot write any equations for mass A alone. So what I'm going to do now is look at the system here, define our system like this, write a momentum equation, conservation of momentum for A and B, x direction, right positive. And what allows us to write this equation is, as long as we define our system as both masses together, these impulses add to zero. They're an internal force. So those forces are internal forces, they add to zero. So no net impulse on the system. That's going to allow us to write the following equation. This guy's x momentum is going to be mb VB1, and I'm going to go ahead and multiply that by cosine theta, or 3/5, positive because it points right. This guy's x momentum, we're going to have minus MA VA1. No sines or cosines required because that thing points directly to the left. All right, momentum in this picture, we're going to have MA VA2. And then this guy's momentum, x component, would be opposite the angle theta. So we're going to have MB VB2, and I'm going to multiply that by sine of 30 degrees to pick off the x component. And it points left, so that thing's negative. And again, we can put equality between these because of this picture right here. These impulses are opposite directions, same magnitude. They're going to add to zero. So kind of looking this equation over, taking note that they're the same mass, we can write this equation now, and I'm going to put like an NCU for note consistent units, dividing the masses out and putting in numerical values. Let's see, we're going to have VB1, so that's going to be 4 meters per second times 3/5 minus VA1, which is going to be 6 meters per second, equals, and again this divided out, VA2, I would like to know, minus VB2 sine 30. So that's going to be minus 3.7 sine of 30 degrees. So what we can do here is solve this for VA2. So I'm going to take a moment and do that. All right, so we're going to have what, 12/5 minus 6 plus 3.7 times the sine of 30 degrees. Ooh, and something interesting happens. I get negative 1.75 out of that. So VA2 we think is negative 1.75 meters per second. Then our $1 million question here, minus sign. Well, remember at the beginning of the problem, I kind of moved on a little hastily. I just assumed that this was to the right. I knew it was parallel. It was stated in the problem that I borrowed this from. I assumed to the right. However, I'm going to go back now and take a quick little look here. In fact, I've already done this. If I calculate the net momentum for this particle, mv, we've got 3 kilogram-meter per second to the left. And if I take a look at this guy's momentum vector, 4 times 0.5, we end up with 2 kilogram-meter per second. Now you notice that 2 is less than 3. On top of that, by the time I multiply that by 3/5, I get something even smaller. So it turned out the net momentum of the system was to the left. Had I looked at that more carefully, maybe I would have drawn this vector to the left, but it doesn't matter. I assumed right. We ended up with a minus sign. We now know that that velocity is 1.75 meters per second left. This is what we know. If you were working this problem and you went back and changed this, that would be fine, but you'd have to go back and change all your work. I'm just going to leave it exactly the way it is and keep going. As long as you're consistent in the problem, everything will work out just fine. All right, so we know VB2, we know VA2. Now it's just a matter of calculating our coefficient of restitution. So I'm going to do that right here. And all we got to do is put in the numerical values. When we do this, however, remember, the coefficient of restitution only applies in the normal direction. Right? We got to keep that in mind when we do this. All right, so VB2, normal component, and the normal component is to the right. So this term right here is going to equal VB2 sine 30, and it's to the left. So I got to look back here. Let's see, VB2 is 3.7, so this is going to be minus 3.7 sine 30 degrees for this guy right here. The minus sign is because that points to the left. The sine 30 is because the coefficient of restitution only applies in the normal direction. So basically we're looking for the x component. Minus VA2. Now, VA2 doesn't have any sines or cosines, but the numerical value, based on the way I have this picture, is minus 1.75. Just be consistent. Over VA1. So I look over here, VA1 is negative 6 meter per second, minus VB1, keeping in mind we only want the normal component. So VB1, the normal component, is going to be minus 4 times 3/5. So what we do now is go through and calculate a value. Now I know with all these minus signs you might get a little bit nervous here, but I'm pretty sure when you work this out very carefully it ends up being positive. And I get, when I work this, I think I got positive 0.11. Let's see, we're going to have 1.75 minus 3.7 times the sine of 30 degrees. So I end up with negative 0.1 in the top. Then the minus sign would cancel that, making it positive 0.1. So then I'm just going to divide that by 6 plus 12/5. And I get 0.0119 out of that, or I'm going to round that. I'm going to say that that's going to be approximately 0.012. Coefficient of restitutions is a dimensionless quantity. You know, take a little note about that numerical value. Very close to 0. You know, coefficient of restitutions are between 0 and 1. 0 basically means they're stuck together. 1 means completely elastic impact. You know, so this is very close to a stuck together type of situation. You know, a lot of deforming must have taken place during this impact. So hopefully this example demonstrates a little bit about how to write momentum equations. You know, it's not a super complex example, but I think it very nicely demonstrates, you know, in the first part, how to write a momentum equation, or where you can write a momentum equation for only one mass. Right? So here we were able to write a momentum conservation for only mass B based on the fact that that exact impulse vector right there does not have a tangential component. That's what allowed us to write a conservation of momentum for that mass in the tangential direction. We could have also written a tangential momentum equation for this, but it would have been pretty boring. We would have had 0 equals 0, so that wouldn't have been any use. Right? Another equation we're able to write is a momentum conservation for the system in the x direction. And this one we can write, we can put that equality there because these two impulses, this one and this one, add to 0. So remember, when you're analyzing impacts, always do the following. Draw a picture of the system like a snapshot right before impact. Always draw the momentum vectors. Draw a picture of the system after impact, drawing the momentum vectors. If you don't know a direction, just guess like I did here. If you in fact guess wrong, it's perfectly fine. What will happen is a minus sign will show up, which allowed me to interpret my answer anyway. I know that that's actually 1.75 meter per second left. If that occurs, don't change your picture. I recommend just keep going and just be consistent. Write your equations assuming this thing's to the right, but then later on when you put in numerical values, just put in a minus sign. Make sure you always draw the impulse picture. This really helps with the type of equations we can write. It will tell you which direction, if you're carefully, you can write individual momentum conservations. It will tell you which direction, right, the normal direction here, you can apply coefficient of restitution. Right? Write your equations accordingly, being very cautious and careful, and hopefully they all work out for you. Right? Everybody have a great day.